series connection. From the circuits above, if you look, you will see that the capacitor, they are connected in series. You can see the way. Now, remember in parallel connection, we said something. We talked about the voltage being the same. And we said that the charges in parallel connection, they are not the same. Now, what is happening in series connection is the voltage are not the same, but the charges are the same. Now, I've already written it here. Remember in parallel connection, I made a statement. I said that for you to get the equivalent or combined capacitance, it is just the summation of the whole capacitance. Now, in series connection, what is happening here is that the equivalent or combined capacitance is just the inverse. Look at it here. And I went ahead and said, if you have two capacitors arranged in series, that the easiest way for you to get the equivalent or the combined capacitor is first the product of the two capacitors, and when you sum them together. Look at it here. Now, in the course of this video, I will be doing a lot of examples for you to catch up what I'm saying. Remember, if the voltage are different, it means that the voltage here in the circuit 1, the capacitor 1, is different from the voltage that is here. The voltage here is different from the voltage that is here. And that is why I said, if I ask you to calculate the voltage in V1, it means Q. You can see I already wrote Q, not Q1, because the charges are the same. But you can see that I wrote C1 because they have different voltage. The same thing applies if I ask you to get V2. V2 is Q all over C2. And if I ask you to get C3, it follows the same trend. Example number 1. The three capacitors, each of capacitance 18 microfarad, are connected in series. Now, calculate the effective capacitance of the capacitor. Now, they said there are 3. So, we have 3 capacitors and they are all connected in series. Right? And each of them are 18 microfarad. Now, remember, the effective capacitance is 1 all over C, 1 all over 18, plus 1 all over 18, plus 1 all over 18. And so this will give you 18, the LCM. Here is 1 plus 1 plus 1. This will give you 3 all over 18, right? So 1 all over C is equals to 3 all over 18. Now, remember what we want to calculate is the C. And so if you can cross multiply, C is equals to 18 all over 3. And that will give you 9. That should give you 3 divided by 18. That should give you 6 microfarad. And that is the answer. Let's go. Number 2. Two capacitors of 6 microfarad and 8 microfarad are connected in series. What additional capacitance must be connected in series with this combination to give 3 microfarad? Now, remember, the total capacitance they gave us to be 3 microfarad. Now, the additional capacitance, let me call the additional capacitance to be X. Now, remember, since there are 2, on a number is supposed to be 1 all over C, 1 all over CT should be 1 all over C1 plus 1 all over C2. Now, remember the additional capacitance, I said let it be 1 all over X, right? So, the total capacitance is 3. So, we have 1 all over 3. The C1 is 6, 1 all over 6, plus the C2 is 8, right? So, 1 all over 8. The additional one is, we don't know it, so let me name it X, right? Now, from this place, look at it. I want to collect let me collect like times here first. So, let me bring this up. So, we have 1 all over 3 minus is crossing the equality sign. 1 all over 6 minus 1 all over 8 is equals to 1 all over X. The LCM between these 3 numbers is 24. 3 will go into 24, 8. 8 times 1 will give you 8. Minus, this will go into this place 4 times. 4 times 1 is 4. 8 will go into this place 3 times, right? So we'll remain with is equals to 1 all over x. 8 minus 4 is 4. 4 minus 3 is 1. So you have 1 all over 24 is equals to 1 all over x. By cross multiplication, S is equals to 24 microfarad. So the additional capacitance is 24 microfarad. Number 3, we have a diagram here. From the diagram above, calculate the PD across C1, C2, and C3. So this is C1, C2, and C3. Now, remember in series connection that the potential difference, they are not the same, but the charges are the same. So the first thing we need to do is get the total or combined capacitance. So which is 1 all over CT is equal to 1 all over 2 plus 1 all over 6 plus 1 all over 3. The LCM is 6. This into this will give you 3 plus 1. This into this is 2. 2 times 1 will give you 2. So 1 all over CT is, this is 6 all over 6. So that means the RP is 1, right? Now remember that Q is equals to CV. This is charge, this is the capacitance, and this is the potential difference in volts. Now, for me to get the charge of the circuit, the capacitor, which is 1, times the volt given here to the 12 volts. So the charges here, the charges is equals to 12 coulombs, right? Now, from here, we want to get the voltage, which is different. So from here, V is equals to Q all over C1. So V1 is Q all over C1. V2 is Q all over C2. And V3 is Q all over C3. Let me write V3 here. So V3 is Q all over C3. Now, from here, V1, remember I'm putting only QQ because the charges are the same. So this will give you 12 divided by the C1. C1 here is 2, and that will give you 6 volts. Here you have 12 divided by the C2 is 6, and that will give you 2 volts. So V3 is Q all over C3. 12 divided by 3, that will give you 4 volts. So automatically, the voltage across C1, C2, and C3 is just 6 volts, 2 volts, 4 volts. That is the answer to this.